Oh. Let's see if I can get this a little more appropriately angled here. That's pretty good. Looks pretty good. Sorry. Okay. Like your shirt? It's a great shirt. That's good. A fan. Let's see here. Do another thing. Why hand I'm ready blue? Oh, I don't know. It's there we go. Chat. And you all have a test next Wednesday, right? Yeah, I asked this last time, and someone was like, "What?" Yeah, that's right. Well, okay, so that means Monday I should think about review. I should write myself a note.
Do you have access to the old midterms? That's like on our canvas.
I probably do, yeah. Yeah.
She gave us some of the.
Okay. We can certainly look at those if that's what you guys all want to do. But yeah, so Monday we'll plan on. Oh yeah, that's what I was thinking, but like, what are we gonna do Wednesday though? Because Wednesday, some of you will already have the test and some of you will not. I'm gonna have to think about this. We'll probably just review both days, and people that don't want to come Wednesday don't have to come Wednesday, I guess. Yeah, that'll probably make the most sense. Okay. Okay. Oh goodness. All right. Sorry. Okay. We gotta actually do some stuff Wednesday, so we might not. Yeah. Okay. We may or may not get to 5.4. Well, that's actually what I was just contemplating in my head. Is like we got actually to move semi-rapidly. So we're gonna start with some 5.3 stuff, and then we'll try to. But I think we should be able to get to 5.4. So yeah, I'm gonna say yes. So let's talk about 5.3 for a second, which is broadly titled log integrals, which is maybe not the most descriptive way of saying it, but it works. So, first of all, I did promise you all something that has to do with log integrals, and so I do want to show you one thing first, which is the following. Where'd you go? I wrote some notes. So something to be aware of. Typically, when you take a derivative of a function, the domain of the derivative is smaller than or equal to the original domain. For example, f of x equal to the square root of x. The domain is everything from 0 to infinity inclusive, whereas the derivative, which is 1/2 x to the negative 1/2, or if you prefer, 1/2 root x, the domain there is a tiny bit less. You don't actually get 0. And that's because the function's not differentiable at 0. So what I really want to kind of point out is that most of the time, in fact, really kind of all the time, when you take the derivative of a function, the domain should get smaller, not bigger. Now, here's what I want to show you. If your function is the natural log of x, which looks like this. Well, first of all, you can only take the derivative of a function where it's defined. So if we take the derivative of this, f prime of x, the derivative natural log of x is 1/x. It's only technically defined when x is greater than 0. Even though we know that the normal domain for 1/x is really everything positive and everything negative. So we're missing kind of this whole other half of this function here. Right? That's kind of, we're not getting that. So what I want to point out is that when you find the antiderivative of 1/x and get natural log of x, it's kind of like you're doing something wrong. Because you're taking this function 1/x that does have this really large domain, and you're cutting off part of it. You're not getting this left half here. So there's a way to fix that. So here's what I mean. Let's take a look at f of x equal to the natural log of the absolute value of x. And we're actually going to take the derivative. So we already know for sure, derivative of the natural log of x is just 1/x. What we're going to see is it's actually going to be true here as well. So first of all, let's graph this. The natural log of the absolute value of x, here's how you should think of this. This is equal to, well, it's actually a piecewise function. If x is positive, great, nothing's changed. If x is positive, then we just get the natural log of regular old x. The natural log of the absolute value of 5 is the natural log of 5. The natural log of the absolute value of 13 is the natural log of 13. However, if x happens to be negative, then we're going to get the natural log of the negative of that negative number. So for example, if I wanted to find the natural log of the absolute value of -5, I would get the natural log of -5, which would be the natural log of 5. So that's always how an absolute value function kind of works. It takes a positive thing, leaves it alone, takes a negative thing, multiplies by -1 to turn it into a positive thing. So now what we're going to do is we're going to graph it. It looks like this. It looks like a normal natural log graph on the right-hand side with an intercept at 1, 0. And then it looks like it's reflected onto the other side. So on the left, it actually looks like this. It should be symmetric. It might not look perfect. It's definitely not going to look perfect. I mean, come on, I'm a human being. I mean, that's what a robot would say. Okay, so there's our natural log of the absolute value of x graph, defined on the left and the right. And now let's see what happens when we take the derivative. Take the derivative of this. I'm going to do it piecewise. So let's do the bottom piece first, because we know the derivative of the natural log of x is just 1/x. And that when x is greater than 0. But now check this out. If I take the derivative of the natural log of some stuff, I get 1 over the stuff times what? Oh, it's been a while. Derivative of the stuff, okay, which is going to be -1 in this case. But look, that just simplifies to 1/x. So whether x is negative or x is positive, the derivative is 1/x. So it is really, really legitimate to say, oh, the derivative is just equal to 1/x as long as x is not equal to 0. So the graph of the derivative here is exactly what you think it would be. It's your usual 1 over x function, but all of it. You get this piece and you get this piece, which is nice because then what's happening is if you take the antiderivative of 1 over x having this normal domain that is almost everything except for 0, the antiderivative has the same domain, right? It didn't get weirdly smaller. So that's good. We want you want your antiderivative to have kind of the same domain as your original function. And if it was just 1 over x, right? Sorry, if it was just the natural log of the regular x, not the absolute not the natural log of the absolute value of x, you wouldn't be getting the whole entire domain that we want. So that's why when we anti-differentiate 1 over x, we get the natural log of the absolute value of x because we want the domains to match up. So all that to say is when you anti-differentiate 1 over x, you're going to get the natural log of the absolute value of x plus c. Or more generally, when you anti-differentiate 1 over u du, you're going to get the natural log of the absolute value of u plus c. Yes, of course. Sorry. I feel like I'm. Yeah, how am I getting so off here? It's just me. It's just me. Okay. So cool. So then we're just going to look at a bunch of examples for a bit here. So for what if I wanted to find, for example, the antiderivative of 1 over x plus 4? Well, there's two ways to do this. There's the long way and there's the easy way. The long way is to do a u sub. So if you see something stuck in the denominator, that's a great choice for you. So if I'm going to do it the long way, I'm going to say, okay, well, I'm going to let u equal x plus 4. Now, here's the great thing about letting u equal x plus a constant. The derivative of u is just 1. Or in other words, du equals dx. So when I rewrite this integral, it's going to be very, very easy to do the u substitution. We're just going to get the integral of 1 over u du, because dx was equal to du and x plus 4 was equal to u. And the integral of 1 over u is exactly that. It's the natural log of the absolute value of u plus c, which is going to be the natural log of the absolute value of x plus 4 plus c. On the other hand, I feel like we don't need to do all this work here. So I'm thinking we can kind of do this in an easier way. We can say to ourselves, well, what function has a derivative that is 1 over x plus 4? Well, I'm thinking natural log of x plus 4. So I'm thinking the natural log of x plus 4. And then if I do the derivative really quick, what's the derivative of the natural log of some stuff? It's 1 over the stuff times, right. But in this case, my stuff is just x plus 4. So my derivative is 1 over my stuff times the derivative of my stuff, which is just 1. So I can see that, oh, well, that's great. That means this function is my antiderivative, except that I have to slap on some absolute values. So I'm thinking, great, I know this is it, but I really want the natural log of the absolute value of x plus 4. And then, of course, I also have to tack on a plus c. So what I'm trying to impart to you here is that you don't really have to do a u substitution here. You certainly can. It's totally valid. But you're going to be doing so many of these that you're not going to want to eventually. So let's look at another example to see how it can be a little more complicated, but not really that much more complicated. So let's look at something like, I want to find the antiderivative of 1 over 7x plus 5. And here's what I'm thinking. I'm thinking it looks like I've got 1 over a thing. So my antiderivative is probably something like, but not exactly, the natural log of that thing. So here's what I'm thinking. Thinking if my function is the natural log of 7x plus 5, what's the derivative? Well, The derivative is 1 over my stuff times what? Yeah. Now here's the deal. I want the derivative to be the thing I'm trying to take the antiderivative of. That's the whole idea, right? If I'm taking the antiderivative of this to get to a function, I'm taking the derivative of that function to get back to my thing. So I'm off. What am I off by? Multiple of 7. So here's how we're going to fix that. If you multiply something by a constant, and then you take the derivative, that constant multiple just hangs out. So the derivative of the natural log of 7x plus 5 times 1/7 is going to be 1 over my stuff times 7 times the 1/7 still hanging out. And those are going to cancel. So in other words, just like before last class, when you have a multiple of x and you want to anti-differentiate, we typically end up dividing by that coefficient of x. So here, the antiderivative of 1 over some stuff is the natural log of the absolute value of that stuff divided by the coefficient of x. Or you might prefer 1/7 times the natural log of the absolute value of 7x plus 5. And I just want to point out, this is really what we want, right? If you take the derivative of the natural log of 7x plus 5, you get 1 over 7x plus 5 times 7. And the times 7 is going to cancel out the 1/7. All right, you all try this one. Try finding the antiderivative of 1 over negative 2x plus 3. Do it. Write it down. Think about it. I'll give you, I don't have my watch on, so I can't time you. I'll give you some amount of time that is moderately reasonable. Like a minute-ish. I guess there's a clock up there. Okay. Been almost a minute. I've got 1 over some stuff. Now I should be a little more specific. The stuff, so well, we'll see a couple of examples later on, but really, when you're talking about 1 over some stuff, that stuff kind of has to be just a linear function of x. You can't, if it was like 1 over x squared plus 1, that'd be a totally different story. It wouldn't be the natural log of x squared plus 1. We'll talk about that in a minute. But here I'm going to get the natural log of the absolute value of my stuff. And what do I have to divide by? So close. Oh, you know, you're on the right track. Just -2. We have to divide by -2. Because if we took the derivative of the natural log of that thing, you would get 1. Well, in fact, let's write it out. So I'm going to rewrite this as -1/2 times the natural log of the absolute value of -2x plus 3. Let's check and see. So if I take the derivative of what I think is the antiderivative, -1/2 natural log of the absolute value of -2x plus 3 plus c, constant multiples hang out, we get -1/2. And the derivative of the natural log of some stuff is 1 over the stuff times -2, the derivative of the stuff, plus 0, because the derivative of constant 0. And look, the -1/2 times the -2 multiplies to +1, and you're just left with 1 over -2x plus 3, as we should have. So that's why we're always dividing by that multiple of x there, because it's going to get canceled out if we were to go back and take the derivative. Yeah, so we can actually make kind of a very general rule here. And the rule is the following. If we want to find the antiderivative of 1 over mx plus b, it's going to be the natural log of the absolute value of mx plus b divided by what? Or multiplied by 1 over what? Right. And then plus c, of course. For the same reasons, we take the derivative. Well, we can either do it by taking the derivative of 1 over m times the natural log of some stuff plus c is equal to the constant. Derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, which is just m plus 0. And oh yeah, that and that cancel out, and you get exactly that. Or you could do it the long U substitution way. You could totally say, instead, I'm going to do a U sub. U is equal to mx plus b. The derivative of a line is just the slope of a line, which is m. So I guess I'll do it the really long way. Dx equals du divided by m. Oh, look, that's where the division by m is happening. And so then when I rewrite my integral, the integral of 1 over mx plus b dx is equal to the integral of, well, that's my u, and dx is du over m. I can pull the constant out in front and say I've got 1 over m integral of 1 over u du, and that's exactly 1 over m times the natural log of the absolute value of u plus c, which is exactly 1 over m natural log of the absolute value of mx plus b plus c. So it totally works. I should really be circling, yeah. So I want to stress, though, this is only valid if essentially, well, let's look at another example and we'll see what I mean. And then we'll talk about the non-example. Let's say I wanted to find, it's a little trickier when you don't just have a linear thing. So I'll point out that if you had something like the integral of 6 over 19x plus 4 dx, before I start integrating, what should I pull out in front? What can I pull out in front? A 6. I can totally write this as 6 times the integral of 1 over 19x plus 4. I can and should factor that out. Technically, if you wanted to get really kind of weird about it, you could pull out a 1 over 19 as well and make the bottom like x plus 4/19, but you don't really want to do that. No one's asking you to do that. Pull out the easy things. Don't try and make it more complicated. So then, if I integrate this, I'm going to get the natural log of the absolute value of 19x plus 4, of course, divided by 19 plus c. Or maybe rewriting it 6 over 19 times the natural log of the absolute value of 19x plus 4 plus c. But then it can get more complicated. So basically, we're thinking we're going to have a logarithm antiderivative if you've got something on the bottom and its derivative on the top. So for example, if I was going to try to integrate 4 minus x cubed over x to the 4th, is that really what I want? I feel like I'm making some dumb mistake here. That's not really what you want, James. Scratch that. Sorry. What I really want is not that. What I really want is something more like x cubed over 6 minus x to the 4th. That's what I'm looking for. So here it's not like super just natural log answer right away. You have to do a little bit more work here. Here's where you really should do the U substitution. So if it's something relatively straightforward where you just have a constant on top and a linear function of x on the bottom, you can totally use the shortcuts. But if you've got something more complicated like this, we should fall back on our U substitution. So we're going to let u equal 6 minus x to the 4th because the derivative essentially looks like the top. Not exactly, but close enough. Our du is going to be negative 4x cubed dx. I skipped the step of writing du dx equals the derivative and just brought the dx over. And then if we solve for dx equals du divided by negative 4x cubed. So rewriting this, I've got the integral of x cubed over 6 minus x to the 4th times, I'm going to replace dx with what it's equal to, du over negative 4x cubed. And when you do this replacement of just dx, your immediate goal is always to cancel the variable that's below the du, right? That x cubed that's below the du, that should cancel. And it does. If it doesn't, it means you might not want to be doing what you're doing. Not 100% of the time, but often. And then the remaining 6 minus x to the 4th is just our u. So what I really have here is the integral of 1 over u times du over negative 4. I would pull out the 1 over negative 4 and write it as negative 1/4 times the integral of du over u. And that's going to be negative 1/4 natural log of the opposite value of u plus c, which is negative 1/4 natural log of the opposite value of, let's see, our u is 6 minus x to the 4th plus c. Cool. So u subs, they're in there. A couple things that do not have a logarithmic antiderivative, just as a reminder. So if instead we had something like, let's see, we had the integral of 1 over 3x minus 1 squared. I'm going to tell you right off the bat, this is not equal to the natural log of the opposite value of 3x minus 1 squared plus c. And the way you can tell is by taking the derivative. If we take the derivative of this, the derivative of the natural log, I'm going to drop the opposite values. And actually, you can totally drop the opposite values here because if you've got something squared, it's going to be positive anyway. So I don't need the opposite values. So the derivative of the natural log of 3x minus 1 squared, I can actually bring that 2 down in front and say it's the derivative of 2 times the natural log of 3x minus 1, which is 2 times 1 over the stuff times the derivative of the stuff, which is 6 over 3x minus 1, which definitely is not 1 over 3x minus 1 squared. So that's not the antiderivative because its derivative isn't the thing you started with. To anti-differentiate this, you would just do a u substitution. You could probably get away without even doing the u substitution, but really to do something like this, you would say, oh, I'm going to rewrite this as 3x minus 1 to the negative second. And then I'm going to do a u sub. I'm going to let u equal the 3x minus 1. Du is equal to 3 dx. So dx is du divided by 3. When we start replacing stuff, this is just going to equal the integral of u to the minus second times 1/3 du, or du over 3. And that's just a straight anti-power rule. The antiderivative of u to the minus second is u to the minus first over minus 1 times 1/3 plus c, which is going to equal, I would probably rewrite this as negative 1/3 times 3x minus 1 to the negative 1. No logarithms in sight. So very, very specifically, to get a logarithm as your antiderivative, you kind of have to have the derivative of the bottom over the bottom. So, and that's what we've always had before, right? In all these examples that we started off with, right? You really do kind of have, like, I know it's kind of weird, but the bottom is 7x plus 5, and the derivative of the bottom is 7, which as long as you've got a multiple of it, you're good to go. Okay. One more example, just as a reminder that these don't always come out to be logarithms. If I wanted to find the antiderivative of 1 over x squared plus 1, which may or may not, oh, this is 16B, we might have talked about this. I should be, no, you might have, I feel like you've seen this. Well, let me tell you what it's not. It's not the natural log of the opposite value of x squared plus 1 plus c. Because we know that if we take the derivative of this, we're not going to get that. if I take the derivative of the natural log of x squared plus 1, what's the additional factor that I'm going to get that is unwelcome? Or what am I going to multiply by after I do the 1 over x squared plus 1? Yeah, that's not the same as that. It's not the antiderivative. So just be careful, right? If you think something if you're not sure about something, you can try to check by taking the derivative of the thing you think it might be. And remember the chain rule. I will tell you, just so you know, you probably saw this last quarter, but I'm not 100% sure. The antiderivative of 1 over x squared plus 1 is the arc tangent of x, or if you prefer, the inverse tangent of x. If you haven't seen this, it's not a big, I'm not going to, you shouldn't worry about this if you haven't seen it. Like, it's not a huge deal, but occasionally sometimes this comes up. So just want to make you aware of it. I think it's more in the 17 series and the 21 series that this comes up, but if you haven't seen it, don't sweat it. It's not gonna all of a sudden appear for you, but just so you know. Time is it? Yeah, okay, wow. Short on time. So let's look at one more example here, and then we will move along. So let's say we had, the integral of 3x plus 12 over 2x squared plus 16x plus 2. Definitely can't simplify that thing. My denominator was way too complicated. So this is the point where, well, I just start guessing things for you. And I'm going to guess the denominator because, well, it's definitely a higher power than the numerator. So if I have something that's one higher power than the other thing, usually the higher power thing is the better choice for you. Also, it's the thing that's stuck, right? 3x plus 12 is technically not stuck. It's just in the numerator. But 2x squared plus 16x plus 2 is definitely stuck. So let's let that equal u, and let's find du, which is 4x plus 16 dx. So this is where methods vary. I guess I'll still, so I want some parentheses around here. Also, I should just reiterate, all I'm doing when I'm finding du is I'm just finding the derivative and then tacking on the dx. I'm just skipping the step where I write du dx equals the derivative. I'm moving it over because it's time consuming. So then I'm going to say that dx equals du over 4x plus 16. But it's going to be really helpful to actually factor out constants. So I'm going to rewrite this as the integral of, so instead of dx, I'm going to write du over 4 times x plus 4. And in the numerator here, I'm going to write 3 times x plus 4 to make it a little more obvious that things are going to cancel. And like always, when you replace dx with du over some stuff, your goal is to make not all the stuff, but definitely the variable stuff should cancel out. If it's not canceling out, you're probably not going to be able to complete the u substitution this way, or maybe at all. But then we're left with, let's see, the integral of, I've got a 3/4, which I'm going to pull out in front. I've got a du on top, and my denominator, that is what we selected for u. So we're back in a du over u situation, and the integral of du over u is just the natural log of the absolute value of u plus c. So we're going to end up with 3/4 natural log of the absolute value of 2x squared plus 16x plus 2 plus c. I will point out, it's not a huge deal, but I'm going to point out anyway. Sometimes with an answer like this, you'll see people drop the absolute values. And the reason they do, like if you look at the solutions manual, and if this was your specific question, and I would not be surprised if they wrote this with the parentheses instead of an absolute value. And here is why. Here I can totally drop the absolute values because 2x squared plus 16x plus 2 is always a positive number. I feel like I'm lying to you there. That feels wrong. Let me double check that. B squared minus 4ac. Oh no, that's a lie. You wouldn't drop the absolute. Sorry, you wouldn't drop the absolute. You could not. Sorry, I take it back. 100% take it back. So you wouldn't drop. But like for example, if you were integrating, just as a real quick one, if I was integrating 2x over x squared plus 1, the integral is going to be the natural log of the absolute value of x squared plus 1, because its derivative is exactly 1 over x squared plus 1 times 2x. And here you might see people drop the absolute values because x squared plus 1 is already always positive, regardless of whether or not taking absolute value. So sometimes people just drop them. If you want to be safe, just never drop them, because then you have to worry about it. But you might see people do that, or solutions manuals do that. Okay, so that's mostly all there is to the logarithmic integrals. There's some other funky stuff, but I feel like we should, since today's Friday, then Monday, and then you have a test on Wednesday. And when's your next homework assignment? Yeah, so the next homework assignment is due Monday. So we kind of talk about, okay. I feel like your professor's kind of been pushing things back, like sometimes, like, 'cause I've seen dates on homework assignments change. Yeah. So is your professor confident that your test is actually going to be on Wednesday? Okay. All right. Good to know. So let's look at section 5.4. And let me kind of reference your homework assignments as well, just so I can not go too off track here. So section 5.4 is where we're going to start actually moving into the area under the curve. So here's what I want to say. So section 5.4, fundamental theorem of calculus. I should actually, let me do one brief calculus. I can spell. Yeah, I can spell. Let me look at one thing really quick on your homework here to see if you have any of those types of problems. No, good. We're only doing that stuff. Cool. So there are two parts to the fundamental theorem of calculus, but we are only using one part of it currently, at least in this section. And really, I'll just be honest with you. We have talked a lot about one of the parts already. One of the parts of the fundamental theorem of calculus is just that the antiderivative and the derivative undo each other. We've seen that a lot already. You already know that part of the fundamental theorem of calculus. The other part of the fundamental theorem of calculus, also known as the evaluation theorem, is just how to use the antiderivative to calculate the area under the curve. So here is kind of the big deal fundamental theorem of calculus, which says the following. If you've got some function like this, f of x, and you want to find the area under the curve from A to B, then we can say that that area, which we typically write as the area under the curve from A to B of f of x dx, or read as, and actually it's good to read this as this is the integral of f of x from A to B with respect to x, right? That's what the dx is, but and that's going to equal capital F of B minus capital F of A, where capital F of x is an antiderivative of little f. That's the whole shebang. That is the fundamental theorem of calculus, part 2. Is it possible to go over homework problem 8.5, number 4? Probably. Take a look. Oh yeah, I'm gonna do one very similar to that for sure. So I want to do. I'm gonna make it a little bit different, but yeah. So this is the whole thing. Now, notably, one thing that's notable is that I said an antiderivative, not the antiderivative, because as we've seen, there are multiple antiderivatives, right? If your function is x to the third, one of the antiderivatives is x to the fourth over 4, another one's x to the fourth over 4 plus 2, another one's x to the fourth over 4 plus 3, right? You can just keep on adding a constant and getting a different antiderivative. The nice thing about definite integrals, where we're finding area under a curve, is you don't need the plus c. You can totally leave it off. And we saw an example of that a few days ago, but I'll remind you of it now. So let's look at some examples. Let's say we wanted to find the area under the curve from, sure, I'll do this one, from 2 to 5 of, let's make it not too terrible, James, 3x plus 7. So I'm going to show you, let's go. I want to pick nicer numbers, but it's fine. Sure, let's go from 2 to 6. So here is how we're going to be doing this. The way you were meant to do this is to find the antiderivative. So the antiderivative of 3x is 3x squared over 2. And the antiderivative of 7 is 7x. No plus c needed. And then typically the notation for this is we say evaluated from 2 to 6. And then you plug in the top thing first, subtract, plug in the bottom thing second. So this is going to equal 3 times 6 squared over 2 plus 7 times 6 minus 3 times 2 squared over 2 plus 7 times 2. So I just want to point out that this right here, this is my capital F of x. It's my antiderivative of little f of x. And this right here is my capital F evaluated at b, and this is my capital F evaluated at a. And then we just do it, right? We actually try and calculate things. So it's going to be not super nice, but whatever. We're going to get 3 times 36 over 2 plus 7 times 6, which is 42, minus 3 times 4 over 2 plus 14. 36 divided by 2 is 18, and 3 times 18 is 54. So we get 54 plus 42 minus 3 times 2 is 6 plus 14 is 20. So we're getting 96 minus 20, which is 76. And that is the area under the curve. In fact, let's take a look at the picture. So if I was actually going to draw this, it would look something like, I don't know, something like that, where this is the point 0, 7. And if I plug in 2 to y equals 3x plus 7, I plug in 2, I get 6 plus 7, which is 13. If I plug in 6, I get 18 plus 7, which is 25. So all we have done is found the area under this straight line from 2 to 6, which we could totally use geometric formulas to also calculate. So I want to point out, you can't always, or usually often, use a geometric formula to calculate area, but sometimes you can, and it's nice to kind of see the correspondence. So just to point out here, this is a rectangle whose height is 13, whose base is 4. So 4 times 13 is giving me 52. And this is a triangle whose base is also 4 and whose height is 25 minus 13, which is 12. And that area is going to be 4 times 12 divided by 2, which is 24. And 24 plus 52 does give us 76. So it's correct, right? The process we did over here actually gave us the right number. And it always will give us the right number, provided that the function you're finding the area under the curve for can actually be anti-differentiated. So that's the general process. Take your function, you anti-differentiate it, you get a number, right? So also pointedly, up until now, every time we've done an antiderivative, our answer was a function, right? We got some function typically of x. Here, our answer is a numerical value. It is the area under the curve. Okay, let's look at a couple more examples. What time is it? Not a lot of time. Okay, I should definitely try to hit that example though. So let me point out one that's similar to question number 9 from the homework assignment covering this material. So let's say I wanted to calculate the following. The integral from, let's make it fun. Let's go from negative 11 to 11 of, let's make it even more interesting. Sure, yeah, that's fine. Of the square root of 121 minus x squared dx. That's what I want to find. Now, here is something worth knowing. I don't think we ever learned how to anti-differentiate this function in class. It's probably not in our syllabus. It's just not there. It's fine. We don't need to. how do we find the area here? Well, here's the thing. If someone asks you to find an integral, unless they specifically say to do it using the fundamental theorem of calculus, I mean, you have to anti-differentiate it. All they're really asking you to do is finding the area under the curve. And typically they will make it clear that you're allowed to use whatever methods, whether fundamental theorem of calculus or geometric, that you have at your disposal. So sometimes, like in the previous problem, you have a triangle and a rectangle, you can find those areas down together. And it's probably not much easier to do it that way versus what we did first. But for a problem like this, which we cannot anti-differentiate without some other tools that we don't have, we can say, oh, but look, I know what that graph looks like. If I graph y equal to the square root of 121 minus x squared, you might not remember what that looks like the way it's written currently. So I'm going to fix it. I'm going to square both sides. I'm going to add x squared to the left. And then I'm going to ask everybody, what kind of graph does x squared plus y squared equal to 11 squared? What kind of graph is that? It's a circle. And it's centered at the origin. Center at the origin with a radius of what? And I picked kind of a big number. How would I find the radius? Square root of 121, which is 11. Which even if you didn't know was 11, like numerically, you would have a pretty good guess that it was going to be 11 because those are your limits of integration. So it's a really good possibility that those are going to be, that radius is going to be 11, because if it wasn't, you wouldn't really be able to calculate the thing. So here is what this, now I should say one more thing. This is the whole circle, top and bottom. This is just the top half of the circle, because if y equals the square root of something, square roots only give you positive outputs, so y has to be positive. So here, this integral, this is just the area under the top half of the circle of radius 11. Well, great. I know how to calculate that. How do I find the area of a circle? Isn't it like, isn't there something with a pi in there? Area of a circle, pi times the radius squared. But I don't have the whole circle, I have the half of the circle, so I divide by 2. That's it. That is what you're expected to do for a problem like this. There is no other good way of doing it. I will also mention, if instead the integral was from -11 to 0 of the same function, well, then I only have this side of it. So I just have a quarter of a circle. So it's going to be 1/4 pi times my radius squared. So if you see something that looks like the integral of the square root of probably a square number minus x squared, you should think circle, circle, circle.
Can you explain again why we're not concerned with the negative part of the circle under the x-axis?
Well, because so the thing is here, if I pick a value of x and I plug it in, y only gets me a positive value. The real reason is because we want this to be a function. And so, right, if you have y equal to this, it's only the top half, because if you had the bottom half, it wouldn't be a function. You violate the vertical line test. You're welcome. Yeah. And let's see, what else have I got here? Yeah, cool. So the nice thing about this is, if you're okay with anti-differentiating things, this is kind of just one additional step. One big additional step where you're just plugging in some numbers. So it's not really any more calculus, right? You already know how to do the calculus part of these problems. The remaining part is just the arithmetic. It's plugging in some numbers and evaluating some stuff. For example, if I wanted to find the integral from, say, 1 to 6 of 1 over x dx, which looks like this. I'm finding that area under the curve. We know how to anti-differentiate 1 over x. That's going to equal the natural log of the absolute value of x from 1 to 6. And then we just plug in. And we get the natural log of the absolute value of 6 minus the natural log of the absolute value of 1. Now it's totally unnecessary to write the absolute values there because the absolute value of 6 is 6. And the absolute value of 1 is 1, and the natural log of 1 is 0. So really this is just equal to the natural log of 6. That's how much area is under that curve from 1 to 6. Square units, I guess, if you want to be interesting about it, but we don't really care. Let's look at, we got time. Let's look at a couple more examples. Let's say we wanted to find the integral from 0 to 3 of x squared minus 9. Okay, same process. Antidifferentiate. The antiderivative of x squared is x cubed over 3. The antiderivative of 9 is 9x. I don't need a plus c. You could write it. In fact, let's write it this one time. And then we're evaluating between 0 and 3. So I'm first going to plug in, it's always the top first. You always plug in the top first minus the bottom second. So it's going to be plugging in the top, 3 cubed over 3 minus 9 times 3 plus c, minus plugging in the bottom, 0 cubed over 3 minus 9 times 0 plus c. Word of warning, a lot of the time when you plug in 0, you get just 0 back, but not always. Like if your function was e to the x, e to the 0 isn't 0, it's 1. Or if you have like a cosine of x, cosine of 0 is 1, not x, not 0. So don't just assume that when you plug in 0, it's all going to be 0. A lot of the time it will be, but not always. So here, what do I get? Let's see. The c's are going to cancel, right? I've got 27 over 3, which is 9, minus 27, plus c, minus 0, plus 0, minus c. The c's definitely cancel, and they'll cancel every time because you're always just adding it and subtracting it. So you end up with negative 18. What does it mean that we have a negative area? It means that more of the area was below the x-axis than above the x-axis. In this case, all of it is. So if you actually graph this, x squared minus 9 is a regular usual problem that's shifted down by 9. So what we actually just calculated was this. We found the area under, or I shouldn't say under, because it's not really the right interpretation, but you're finding essentially the area between your curve and the x-axis. An area that's above the x-axis gets counted as positive, an area that's below the x-axis is counted as negative. Now, it's not something that you have to be specifically worried about because when you do the integral, it'll just come out to be the right thing. So if your curve was under the x-axis, your integral will end up giving you a negative value. If your curve was above the x-axis, your integral will end up giving you a positive value. Let's look at one more example. Yeah, we got time for one more example, just to show you one more cool thing or useful thing. What if I wanted to find the integral from, sure, let's do that. The integral from 0 to pi of cosine of x. So first I'm going to draw it for you. I'm going to try and do a good job. So let's see, pi, 2 pi, pi over 2, 3 pi over 2. And cosine looks like this. It starts at 1 and then goes to 0, it's -1, and then back to 0 and then back to 1. So cosine has this kind of shape. So I'm going from 0 to pi. I'm looking at all this and all this. So if you had to guess what this integral was going to equal, what might you guess?
0.
You might guess 0, and you would be right because the area on top getting counted positively and the area on the bottom getting counted negatively are exactly mirrors of each other, and they're going to cancel each other out. Let's do the calculation then. If we anti-differentiate cosine of x, we get positive sine of x. From 0 to pi, we plug in, we get sine of pi minus sine of 0, but sine of pi is 0 and sine of 0 is 0, so we get 0. So if you have the same amount of area above as below, they do end up canceling each other out. And essentially, you could take all the positive areas and subtract all the negative areas, and then you have the net area. So really, when you're integrating a function from a to b of f of x dx, it is the net area under f of x that is above the x-axis. That's the more precise geometric interpretation of what an integral is. But even if you're not super comfortable with the interpretation, the calculation is still relatively straightforward from what we've been doing. You're just using all of your anti-differentiation tools. Now, I know we didn't do any use substitution examples, but you can also use examples of use substitution, which we'll do on Monday. Yeah, we have to talk about this more on Monday. So we'll talk about this more on Monday. And then how many of you have the test before this on Monday? Yeah, okay, well, we'll figure something out. I'll think about it. But I feel like we should talk more about this on Monday because you will have this homework due on Monday, right? Yeah, and yeah, we'll see. We'll see what I can come up with. But yeah, oh, what I was saying is, even if the physical geometric interpretation is not super solid for you right now, the calculation is still not something foreign to you. We have had lots of practice finding antiderivatives. The only thing you're doing now that's extra is plugging in the top value, subtracting, plugging in the bottom value. That's not too much of an extra thing to do. All right, I have to stop talking. I have office hours over in CADS from whenever I get there to 4 o'clock. And have a nice weekend. So to answer the question, so there's a question about attendance, and just to answer your question, if you fill out the form, eventually it will get updated. I've been having a lot of other work I've had to catch up on, like grading for the other class I teach. So if you fill out the form and it hasn't, as long as you haven't been marked absent, it means I just haven't updated the like if your attendance grade hasn't changed, because it hasn't in like a week, it's because I just haven't done it yet. So I'll get there. You should keep filling out the form. I will eventually update things. It's just on the back burner right now because I got other things that are more important. Yes, I'll get that sorted out. Cool. See, make sure everyone is good. Yeah, all right. Right. Should get there. Have a nice weekend.